We saw when using Euler's method that the scheme was globally first order accurate. That means if we change the step size in the method, the error only decreases proportionally to the step size. So if we halve the step size, the error gets half the size. Generally speaking, that is not good enough for most computations, so we need methods that are more accurate. Heun's method is one of these methods. It's something that we did in Eng 1060, so I'm not going to spend a long time doing this. So we start off with the ODE, the generic ODE. dy dt is equal to some function of t and y, and the solution is represented in that figure on the right hand side. If we know the solution y is equal to yi when the time is equal to ti, that's the red point just there, then the solution y is equal to yi plus 1 at t is equal to t plus 1 can be found with a single step of Euler's method via the following equations. yi plus 1 is equal to yi plus h times the right hand side function evaluated at the beginning point, in other words ti yi. So we take the slope, we take a step size of h, and we jump forward following that slope, where this thing here is the step size h. Euler's method assumes that the slope at y is equal to ti yi is a good approximation for the entire interval, and by and large this is not a good approximation. Heun's method aims to improve on this by estimating the average slope using the following. The value at the beginning of the step, that's the slope that we have there, and the value at the end of the step, that's the value that we'd calculate there. We have everything we need at the start of the step, so we know what ti is, we know what yi is, but to find the slope at the end point of the step, in other words the function value at ti plus 1, yi plus 1, we need to know what yi plus 1 is equal to. But that's the thing we're trying to find in the first place. So we can't possibly use Heun's method exactly like this, using that kind of functional form. We need to do something a little bit different. So let's estimate the value of yi plus 1 using a single Euler step. So we go to the point ti yi, we calculate the function value there, the slope of our solution. We take an Euler step, so we go to the end of the step, and we calculate a solution that we're going to call yi plus 1, 0. And that superscript 0 just means it's a guess for the solution. It's not the solution that we're actually going to come up with. So that's this point here. So that's a single Euler step. That gives us an estimate. Then what we can do is we can estimate the slope at this end point by substituting yi plus 1, 0 into our right hand side function. So if we can estimate this slope at the end there, we can say it's approximately going to be equal to the actual slope at the end point. There will be an error associated with that approximation. So now we average the start and the end values of the slope. Take them back there, we calculate the average value, so it points somewhere in between these two. We can then say that slope is given by 1/2 the value at the beginning plus our value or approximate value at our end point there. We can then take the average slope on the right hand side of an Euler type step to give the solution yi plus 1. So we say that yi plus 1 is equal to yi plus h times the average of the slope at the beginning and the slope at the end. And that's where the factor of 2 comes in. This is Heun's method. It's a type of scheme known as a predictor-corrector scheme. So in the predictor step, we do an Euler update. It calculates a guess for the solution using a step size of h. We know that this is not correct. We then take that and use it in a corrector step. So in the corrector step, we average the slope at the beginning and our estimate of the slope at the end. And again, this step looks very much like an Euler step. So the thing I've just circled in green is a slope with an h out the front. That's why Euler's method is so important to understand. So graphically then we have these two plots here. The predictor step, where we start at the beginning, we go to the end, and the corrector step, where we've estimated a slope as being the average of the slope at the beginning and an average of our estimate of the slope at the end, and then we move forward a full step from the beginning, from ti to ti plus 1. So far we've only done one step of Heun's method. In practice, of course, we have to do multiple steps if you want to get to the beginning of our solution right to the end. So how do we solve for multiple steps? Well, start off with our initial condition, T0, Y0, and we undertake an Euler step with I is equal to 0 and a step size of h. That gives us an estimate of our solution at the end, and we call that Y10. So basically what we're doing, we're implementing this formula here with I is equal to 0, because it's the first step. We're trying to find y1. We now need to calculate the slope at this point that we've just found. We need to average the slopes at the beginning and the end to get the average value. We then calculate a new estimate of y1 using the corrector step and this average value of the slope that we've estimated. So now we've calculated y1. So we now need to move to the next step. We've got T1, Y1, so we perform an Euler step. Again, we're performing this predictor step here with I is equal to 1. We estimate our solution, Y20, by doing an Euler step with a step size of h. We then calculate the slope at the end point. We average the slope at the beginning and the end point. And we calculate our new estimate of y2 using the corrector step with I is equal to 1. And that's that equation there. So we've now done 2 steps using Heun's method. We perform the next step to try and find y3 by substituting I is equal to 2 into these predictor and corrector steps up there. It's possible to show that the error when integrating from ti to ti plus h in a single step of Heun's method is the error is equal to the second derivative estimated somewhere in the interval divided by 12 times h cubed. The thing that's most important here for us is the fact that the error scales like h cubed. It's order h cubed. That's for a single step. Thus, halving a step size means that the error is going to be approximately 8 times smaller. If we compared the similar thing for Euler's method, it was only 4 times smaller when we halved the step. Therefore, Heun's method is twice as accurate as Euler's method if we halve the step size. Using similar arguments to those that we used with Euler's method, you can show that the global error, now remember the global error is the sum of the local errors and the propagated errors, for Heun's method scales like order h squared. And so Euler's method was order h, Heun's method is order h squared, so it's clearly going to globally be more accurate.